In this lecture, we talk about balancing Tor. So say we are given two R modules A and B. So A has a projective resolution like this, P4 going to P3, P2, P1, P0. Each one of these is a projective module, and similarly we have a projective resolution for B. So recall we talked about derived functor in our lectures on homological algebra. So you take A and tensor it with, say, projective resolution of B, and then you can take homology to get Tor, and like this. So this A is fixed here. So even if you have forgotten the definition of Tor, it will be clear from the context in this lecture. And for the derived functor of this is again Tor here B, and this means that we are tensoring B with the projective resolution of A, and you get another derived functor like this. So the purpose of this lecture is to show that this Tor A applied to B and this Tor B applied to A, they are the same. So that is, this Tor functor does not depend upon the projective resolution of A or B. So the lectures on homological algebra, we just mentioned that the Tor does not depend upon the projective resolution of A or B. So here we use spectral sequences to prove that it does not depend upon the projective resolution of A or B. So again, if you have forgotten what the definition of Tor is and how it behaves, you don't have to worry about it. It will be clear in the lecture itself. So we are given the projective resolution of A and B, and from that resolution we form a double complex. So we have seen the formation of this double complex in a previous lecture. So this is a double complex, and what you get is a total complex. So once you form the double complex, the first thing is you take a vertical filtration. So that is, you will only keep the columns, that is the these orange or rust colored arrows. So let us delete all the green arrows here, and again notice that we will also get rid of these ones, because these ones and these negative ones are going to have no impact whatsoever on the homology, because this, after we delete the green arrows, what we have the page is the page 0, and then we start taking the homology to go to page 1, page 2, and so on. So this is how the vertical filtration will look like. Now keep in mind that each of these PIs is projective because our resolution was projective, and therefore it is flat. So by flatness we means is you take the tensor product like this, you will get an exact sequence. So the following sequence is exact because this PI everywhere is projective, and you are taking the tensor product with the projective resolution of P. As you can see, B is here, and then Q0, Q1, Q2, and so on. So exactness means that if you take the homology of this, everywhere it will be 0. So homology here would be 0, homology here would be 0, 0 here, 0 here, and so on. So all these homologies would be 0, 0, 0, 0, 0. But the problem here is that it will not be 0 here because this goes to 0. Here it is going into PI tensor B. So although you get a 0 homology here because we have this group sitting right here, but here we are just putting 0 here. So there is some non-zero homology here. So what is the homology here? You always know when a sequence ends in 0, the homology here is co-kernel of T. So the homology at this point is co-kernel of this map. So let us call this map D1 to avoid confusion. So this will be co-kernel of D1, the homology here. So and correspondingly the map D1 here is right here. It is going from Q1 to Q0, PI is a constant. So this is how every column looks like. So in here you have 0 instead of PI. So you have P0, P0, P0. Here you have P1, P1, P1. So P1, 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 P1. Here you have P2, 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 P2. So P2, 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 and so on. So this is how our column looks like, and we are talking about how do you find co-kernel of D1. So what is co-kernel of D1? So now I see this ends in 0 because this was a projective resolution, therefore it was flat. You could tensor it with B or projective resolution of B. So co-kernel of D1 is precisely PI tensor B. That is because if this is exact, this map is onto. So if this map is surjective right here, so if it is surjective right here, that means that co-kernel of D1 is precisely this. So by the definition of co-kernel and surjectivity, this holds. So PI tensor with B. So here you will get P0 tensor with B. So here we will get P1 tensor with B. Here we will get P2 tensor with B. Here we will get P3 tensor with B. Here we will get P4 tensor with B. So let us now write it clearly on next page, and everywhere else there is a 0. So these are the only non-zero portions. So here everything is 0, because again the sequence is exact till this point, and after that you have this problem because you have this pi tensor B here which is missing here. So everywhere the homology is 0. So let us rewrite this more clearly. So now from page 0 we have gone to page 1. So we took the homology, and that's what we got, 0 everywhere else, and then on page 1 this is the terms we get. And again recall, our arrow convention is minus r minus 1. So on page 0 we were 0 minus 1, that is 1 down, and on page 1 we are going to be minus 1 0, so that is 1 left. So you're moving 1 left. So the TOR is precisely the homology of this. So that's why I said if you do not know the definition of TOR, to be clear now. So take the homology of this again, you will land up in page 2. So this homology of, so this is a chain complex, and you start taking the homology of this, you start getting TOR. So this is TOR 0 BA, because see B is constant here, and you have the projective resolution of A. So projective resolution of A was in terms of P. So P0, P1, P2, P3, P4, and so on. So you have A right here. So B is fixed. So again you have B fixed. So this is the homology here. This is the homology at this point. This is the homology at this point P2. This is the homology at this point. This is the homology at this point, and so on. So after page 2 you have this TOR lying on our 0th row, q equals to 0. This is also lies on 0th row on page 1. Everywhere else is 0. So arrows going out of TOR go to 0, and arrows going into TOR come from 0. So 0 is going in. So as you know before, if 0 is going in and 0 is coming out, your homology groups have stabilized. So you keep taking homology on page 3. Since 0 is going in and 0 is coming out, it is always the kernel of the map, which will be precisely this term again, because everything is getting mapped to 0. So page 2, page 3, page 4, page 5, all the way to page infinity are the same. So this is also how page infinity will look like. So keep this in mind, that page infinity looks like this. Now we have done this. Let us now see the row filtration. So now if we see the row filtration, we will have to transpose our arrows so that they become columns. So we have to make them columns, because on page 0 our rule is minus r minus 1. So that is r put 0, so 0 minus 1. So the arrow has to go down. So there's nothing going towards the left. So to fit on page 0 we have to transpose our rows to become columns. So this will be clear as we do it. So the arrow should face downwards, which is the convention of page 0. So notice what we mean by transposing. So these were the rows which we have transposed to make it into columns, because this is the convention of page 0. So the arrows face downwards. So notice now in column here, column 0, you have Q0, 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 Q0. The P's are changing. Here you have Q1 is fixed. Here Q2 is fixed. The P's are changing, and so on. So everywhere you have this Qi is fixed. So one column like this you can write like this. So again each of these Qi is projective and therefore flat. So you have this exact sequence like this. So again call this map here as, say, partial 1, and this goes to 0, this goes to 0. So since this is sequence exact, you get 0 here, 0 here, 0 here, 0 here as the homology groups. So everywhere you get a 0. So you have 0 here, 0 here, 0 here, 0 here. The only problem is here this P0 tensor with Qi or Q0 goes into here. Here it goes to 0. So there has to be a non-zero homology group here, because you get 0 in such a sequence and this is missing here. So what is the homology here? We always know the homology here at the last term, which enters 0, is co-kernel of the incoming map. So co-kernel of our partial 1. So this partial 1 sits right here, going from P1 to P0. And again, this entered 0, so therefore this map is onto, so this map is surjective. And since this is surjective, that immediately implies that co-kernel of our partial 1 is precisely this. So the homology here will be nothing but, so from here you can see this is a tensor with Q0. Here it will be a tensor with Q1. Here it will be a tensor with Q2, and so on. And everywhere else you have just zeros sitting. So we are computing the homology, which we are going to put again on page 1 now. So let us clearly see how page 1 looks like. So this is how page 1 will look like. And this is what is sitting on our 0th row. Everywhere else you have 0. So you start taking the homology of this. If you take homology of this, you will land in page 2. And as I said before, the homology of this is precisely what will give you Tor. Again, notice that A is fixed, and this Q0, Q1, Q2 is the projective resolution of B. So just like before, now we have the page 2 of our row filtration. This is how it looks like. Tor 0, A, B, this, Tor 3, Tor 4. Just like here. Nothing much has been done. Exactly. Again, zeros are coming into it and zeros are going out of it. 0 is coming in and 0 is going out of it. So this thing has stabilized. So page infinity will also look like this. So now we start with the total complex or a double complex, and from that we get page infinities. You get page infinity here and page infinity here. So we already know that everywhere else you have zeros on the page infinity. So if everywhere else you have the zeros on the page infinity, our homology of the total page, so the total page is direct sum of anti-diagonal elements, but the only non-zero term is sitting right here on the x-axis on q equals to 0. Everywhere else you have 0. So homology of total complex, if you look at this row filtration, it will give you this. Say instead of Tor 2, I'm going to write Tor star. So this was the homology, because everywhere else you have zeros. And correspondingly, if you see the column filtration, we got this term. So this is equal to corresponding Tor star. So you can see we have been able to prove what we started with. So the projective resolution does not really matter whether you take projective resolution of A or B while defining your Tor.